Hi, for the continuation of the wastewater treatment, now we will discuss the primary treatment. With the screening completed and the grit removed, the wastewater still contains light organic suspended solids, some of which can be removed from the sewage by gravity in a sedimentation tank. These tanks can be round or rectangular. The mass of settled solids is called raw sludge. This sludge is removed from the sedimentation tank by mechanical scrapers and pumps, or it could also be removed manually. Floating materials such as grease and oil rise to the surface of the sedimentation tank, where they are collected by a surface skimming system and removed from the tank for further processing. Primary sedimentation basins, or the primary tanks, are characterized by type 2 flocculent settling. Rectangular tanks with common wall construction are frequently chosen because they are advantageous for sites with space constraints. Typically, these tanks range from 15 to 100 meters in length and 3 to 24 meters in width. Circular tanks have diameters from 3 to 90 meters. Hydraulic detention time in the sedimentation basin ranges from 1.5 to 2.5 hours under average flow conditions. A 2-hour detention time is typical for this primary treatment. So let's solve a problem related to primary treatment. Calculate the detention time, overflow rate, and weir loading of the primary tank given the data. Flow 0.150 cubic meter per second. Influent suspended solids 280 milligrams per liter. Sludge concentration 6%. Efficiency 60%. Length 40 meters. Width 10 meters. Liquid depth 2 meters. And the weir length of 75 meters. From the previous discussion, we learned that the detention time is equal to the volume divided by the volumetric flow rate. Let's solve first for the detention time. Detention time is equal to the volume divided by the volumetric flow rate. So we have a volume of 40 meters times 10 meters times 2 meters divided by the volumetric flow rate of 0.150 cubic meters per seconds. So our detention time is equivalent to 5,333.33 seconds, or equivalent to 1.5 hours. So the question is asking for the detention time we already solved, which is 1.5 hours. Now we are going to solve for the overflow rate, and it is equal to the volumetric flow divided by the surface area. So overflow rate is equal to the volumetric flow divided by the surface area. And we have the volumetric flow of 0.150 cubic meter per seconds. And our area, surface area, is 40 meters times 10 meters. And then we will convert these seconds into day. In 1 day, there are 86,400 seconds. So it's equivalent to 32 meters per day. This is now our overflow rate. Then last is the weir loading. So for the weir loading, it's equivalent to the volumetric flow rate divided by the weir length. So we have 0.150 cubic meter per seconds divided by the weir length, which is 75 meters. Then we will convert the second into day. So 86,400 seconds is equivalent to 1 day. So our weir loading now is equivalent to 172.8 meters squared per day. So we already have the detention time, overflow rate, and the weir loading. Now let's move on to the unit operations of secondary treatment. So we have the activated sludge. The activated sludge process is a biological wastewater treatment technique in which a mixture of wastewater and biological solids is agitated and aerated. The settling tank that follows the aeration tank is referred to as a secondary clarifier or final clarifier to differentiate it from the sedimentation basin used for primary settling. So the biological solids are subsequently separated from treated wastewater by settling a fraction and is returned to the aeration process as needed. So as the microorganisms grow and are mixed by the agitation of the air, the individual organisms clump together to form an active mass of microbes called the activated sludge. In practice, wastewater flows continuously into the aeration tank where air is injected to mix the activated sludge with the wastewater and to supply the oxygen needed for the organisms to break down the organic matter. The mixture of activated sludge and wastewater in the aeration tank is called mixed liquor. The mixed liquor flows from the aeration tank to the secondary clarifier, where the activated sludge is settled out. So most of the settled sludge is returned to the aeration tank to maintain the high population of microbes that permits rapid breakdown of the organic matter. So the activated sludge process is controlled by wasting a portion of the microorganisms each day in order to maintain the proper amount of microorganisms to efficiently degrade the BOD5. A balance is then achieved between growth of new organisms and their removal by wasting. If too much sludge is wasted, the concentration of microorganisms in the mixed liquor will become too low for effective treatment. If too little sludge is wasted, a large concentration of microorganisms will accumulate and ultimately overflow the secondary tank and flow into the receiving stream. So wasting means that a portion of the microorganisms is discarded from the process. The discarded microorganisms are called waste-activated sludge. The mean cell residence time, also called solids retention time, or sludge age, is defined as the average amount of time that the microorganisms are kept in the system. This differs from the hydraulic detention time, which is the average time wastewater is in the tank. This is the conventional activated sludge plant. It starts with the bar rack, then after that it enters the grit chamber, and then primary settling tank or the digester. Then after that it enters the aeration tank, then the secondary settling tank, and the disinfection prior to distribution. Now let's move on to the trickling filters. A trickling filter consists of a bed of coarse material called media, such as stones, flat, or plastic materials, over which wastewater is applied. Trickling filters have been a popular biologic treatment process. The most widely used, designed for many years, was simply a bed of stones from 1 to 3 meters deep through which the wastewater passed. As the wastewater trickles through the bed, a microbial growth establishes itself on the surface of the media in a fixed film. The wastewater passes over the stationary microbial population, providing contact between the microorganisms and the organic compounds in the wastewater. Oxidation pans. An oxidation pan was a pan that received partially treated wastewater, whereas a pond that received raw wastewater was known as a sewage lagoon. Waste stabilization pond has been used as an all-inclusive term that refers to a pond or lagoon used to treat organic waste by biological and physical processes. To avoid confusion, we will use the following classification. We have the aerobic ponds, shallow ponds less than 1 meter in depth, where dissolved oxygen is maintained throughout the entire depth, mainly by the action of photosynthesis. We have the anaerobic ponds, deep ponds that receive high organic loading such that anaerobic conditions prevail throughout the entire pond depth. We also have the facultative ponds, the maturation or the tertiary ponds, and the aerated lagoons. Now let's move on to the rotating biological contactors. The rotating biological contactor process consists of a series of closely spaced discs mounted on a horizontal shaft and rotated while about 1/2 of their surface area is immersed in wastewater. When the process is placed in operation, the microbes in the wastewater begin to adhere to the rotating surfaces and grow there until the entire surface area of the disc is covered with 1 to 3 mm layer of biological slime. The excess growth of microbes is sheared from the disc as they move through the reservoir. These dislodged organisms are kept in suspension by the moving disk. As the disk rotates, they carry a film of wastewater into the air. This wastewater trickles down to the surface of the disk, absorbing oxygen. As the disks complete their rotation, the film of water mixes with the reservoir of the wastewater, adding to the oxygen in the reservoir and mixing the treated and partially treated wastewater. As the attached microbes pass through the reservoir, they absorb other organic compounds for breakdown. Thus, the discs serve several purposes. So they provide media for the build-up of attached microbial growth. They bring the growth into contact with the wastewater, and they aerate the wastewater and the suspended microbial growth in the reservoir. The principal advantages of the RBC, or the rotating biological contactor process, are simplicity of operation and relatively low energy cost. They have found application in small communities. This is the rotating biological contactor and process arrangement. So they have disk, the first stage and the second stage, and the drive motor for the disk. They also have the effluent weir, the effluent discharge, the effluent scoop, the sludge discharge, and the secondary clarifier. Now let's move on to the moving bed biofilm reactor. This process uses small plastic elements to support the growth of biofilm in the reactor. The suspended growth portion of the hybrid is designed as a complete mix reactor. It is commonly mixed with aeration but may also be mixed with a mechanical mixer. The process does not use a return sludge flow. The media is formed in a geometry that provides a high surface area. Because of their shape, less than 15% of the water is displaced. A screen across the outlet is used to prevent the media from leaving the aeration tank. Aeration is typically by coarse bubble diffusers. Now let's move on to the unit operations of tertiary treatment. We have the granular filtration. By using a filtration process similar to that used in water treatment plants, it is possible to remove the residual suspended solids, including the unsettled microorganisms. Removing the microorganisms also reduces the residual BOD5. To lengthen filter rounds and reduce backwashing, it is desirable to have the larger filter grain sizes at the top of the filter. So this arrangement allows some of the larger particles of biological flux to be trapped at the surface without plugging the filter. Multimedia filters accomplish this by using low-density coal for the large grain sizes, medium-density sand for the intermediate sizes, and high-density garnet for the smallest size grains. The conventional sand filters, identical to those used in water treatment, can also be used, but they often clog quickly, thus requiring frequent backwashing. Thus, during backwashing, the greater density offsets the smaller diameter so that the coal remains on top, the sand remains in the middle, and the garnet remains on the bottom. Now let's move on to the carbon adsorption, which is one of the unit operations in tertiary treatment. Even after secondary treatment, coagulation, sedimentation, and filtration, soluble organic materials that are resistant to biological breakdown may persist in the effluent. The persistent materials are often referred to as the refractory organic compounds. Refractory organic compounds can be detected in the effluent as soluble chemical oxygen demand. The most practical available method for removing refractory organic compounds is by adsorbing them on activated carbon. Adsorption is the accumulation of materials at an interface. The interface in the case of wastewater and activated carbon is the liquid-solid boundary layer. Carbon is activated by heating in the absence of oxygen. The activation process results in the formation of many pores within each carbon particle. Because adsorption is a surface phenomenon, the greater the surface area of the carbon, the greater its capacity to hold organic material. After the adsorption capacity of the carbon has been exhausted, it can be restored by heating it in a furnace at a temperature sufficiently high to drive off the adsorbed organic material. Keeping oxygen at very low levels in the furnace prevents carbon from burning. The organic compounds are passed through an afterburner to prevent air pollution. So that's all for the wastewater treatment and technology. Thank you.